Alrighty guys, let's go ahead and get started with this problem. So this says consider a uniform plank to be a heavy slab of wood with a mass of 900 kilograms and a length of 3.6 meters long. Assume the plank rests on the ship at the 2.232 meter mark of the plank. Captain Doves has a mass of 68 kilograms. The crew makes Captain Doves walk to a distance of 2.5668 meters. Assume the board's 0 meter mark is located somewhere on the boat. What is the maximum magnitude of torque the plank can support? So first, let's go ahead and start out by drawing a picture. So if I have my plank, it's probably going to look something like this. It tells me that the captain is located at 2.5668 meters. So probably somewhere over here. We don't know exactly. I'm just going to eyeball it. 2.5668. It also tells me that the entire length of the board is 3.6 meters. And it tells me that the plank is resting on the ship at 2.2332 meters. So this is my pivot point. So I'm going to go ahead and draw that somewhere over here, 2.232 meters. Cool. So we got just about all the information that we need. We have 900 kilograms of plank mass as well. So question number 1 says, what is the magnitude of the torque on the plank? Well, I know torque is equal to force times R if it's perpendicular. Since these are all dealing with gravitational forces, that means that the signs are all going to be 90 degrees. Sine of 90 is just 1, so I can ignore the sign. So the force in this case, like we said, is force gravity. And we know force gravity is just equal to mass times gravity. So the torque of the board should be the mass of the board, which is 900, times the gravitational pull, which is 9.8, times R. The question is, though, what is R for this plank? Well, it's a uniform plank of length 3.6 meters, meaning that its center of mass is going to be somewhere around the 1.8 meter mark. R is not the radius, so it's not going to be the radius of the board or the length of the board. R is the distance of separation. So R is going to be our pivot point minus where the center of mass is located. So in this case, our R value should be 2.232 minus 1.8, which is 0.432. So times 0.432. When I do that, I find out that the torque should be 3,810.24 Newton meters. So it asked me in the question what the maximum magnitude of torque is, and this is the maximum because this is the most torque that our plank can supply given its pivot point. So this would be our answer. Now we're going to take a look at what the magnitude of torque supplied by Captain D is. So torque, we know again, is force times the distance from the pivot point. Force is mass times gravity. So Captain D's mass is 68, his gravity is 9.8, and the R is the distance from the pivot point. So his distance is from here to here. So that would be 2.5668 minus 2.232. That would give him a distance of 0.3348 meters. So I'm going to take that and plug that in for R over here, 3348. Multiply everything through, and I find out that my torque supplied by Captain D should be 223.11 Newton meters. All right, next question. This says, what is the magnitude of the net torque, assuming the plank does not rotate? And we know that the plank's not going to rotate because it says part of it is on the ship, meaning that it can't rotate into the ship. That just doesn't make any sense. So if our plank is not rotating, that means that net torque in this case is 0. The reason we know it's 0 is because, like we said, it's not rotating. It's in equilibrium. But there's several ways to figure this out. If we look up here at our equations, we know that net torque is equal to I alpha. Well, alpha is the angular acceleration, meaning how quickly we are changing the rate at which it's spinning. Well, if it's not spinning, we're not changing the rate. And if we're not changing the rate at which it's spinning, that means that alpha is 0. If alpha is 0, net torque has to be 0. So again, net torque in this case is 0. So this goes back to before, how you guys answered the maximum magnitude of torque here. And some of you might be thinking, wait, hold up. isn't net torque this minus this? Well, yeah, if it was moving, but again, it's not moving. The plank is not falling into the ship. And we said in the question what the maximum magnitude of torque is. This is the maximum amount of torque that our plank can supply. How much torque is our plank supplying? Well, our plank is supplying 223.11 Newton meters of torque right now. And we know that that's our answer because it's in equilibrium. It's not rotating to one side or the other. So think about this in terms of how we thought about friction when we were doing our force unit, how friction had a maximum value it could be. Same thing with the torque of the plank in this scenario. The torque of the plank has a maximum value it can be before the plank tips over. Number 4 says the crew is upset that he did not fall. They start throwing weights at him in hopes of breaking the plank. How much additional mass do they need to throw on the plank at his current location to tip him over? So there's multiple ways to figure out this problem, and we're going to approach it this way. We know that net torque is equal to, assuming that we want to tip him over, it's going to be all these torques added together. So that would be 3,810.24. And since this is going in one direction and this is going in the other direction, I'm going to subtract the other one, 223.11. And then I'm going to add a second torque here. This second torque is going to be the torque supplied by the weights that the crew is throwing at him. We know that that torque is dependent on the mass of those weights as well as gravity, which is 9.8, because that's the force that those weights would exert, times the distance that they are from the pivot point. These weights are the same distance that Captain D is, so that's 0.3348. And we know that if it wants to tip over, that the net torque basically has to be slightly greater than 0, or we can just argue 0, and if a big gust of wind comes over, then it will tip over one way. So I'm going to say that this is really just equal to 0. So if we add this over to the other side, we get mass times 9.8 times 0.3348 is equal to 3810 minus 223, which is 3,587.13. Now to solve for mass, we're just going to divide out 9.8 and 0.3348, which when we multiply those two together is just 3.28. So divide each side by 3.28. These cancel out, and we're left with a mass of 1,093.29 kilograms. So that's one way to solve it. The other way to solve it, let's just do it really quickly, would be to say that the torque of one side needs to equal the torque of the other side. Well, the torque of the plank is 3,810.24, and the torque of the other side is Captain Dubs and the weights. But let's just say that we don't know what either of those are. So that force would be equal to mass times 9.8 times the distance that Captain Dubs and those weights are going to be at, 0.3348. This is a little bit easier to manage. When we do that, we find out that the mass in this case should be equal to 1,161.21. We notice that these are different masses. So hold up, one of these is the right way, one is not. Well, if we pay attention, this is the total mass on the right side. That includes Captain Dubs' mass. So what do we have to do? Well, the question's asking us how much additional mass needs to be added. So we need to go ahead and subtract Captain Dubs' mass, which is 68. When we do that, we end up with the exact same answer that we have on the other side, which is 1,093.2 kilograms. Both ways work. This way just requires us to use our brain a lot more to really understand what we're getting. Last question says the pirates are pretty mad because they don't want to waste all that gold. Therefore, they use a lighter plank to accomplish the same goal. What mass is needed for the plank to tip over when just the captain is located at a distance of 2.5668 meters from the bottom of the plank? So we need to figure out the plank's new mass here. So to do this one, it's essentially the exact same question, except now the torque needs to be equal to just the captain's torque. So 223.11 should be equal to the mass of the plank times gravity, because we know that it's the force that the plank is exerting, times the R, and we know that the R value of the plank is 0.432. So if we do that, we can go ahead and simplify, and we find out that the mass of the plank needs to be 52.7 kilograms.